Hi, this is Dave Johnson with another edition of Math Off Topics. Today we want to address the question of whether it's legal to integrate both sides of an equation. In particular, integrating both sides of an equation with respect to different variables. Now, when you first started learning algebra, the thing that they told you all the time was whatever you do to one side of the equation, you have to do to the other. And if you do that, the reason for doing that is that you preserve the solution set. So you take your original equation that has some solution set. You do something to both sides of the equation. If that algebraic process is legal, your solution set hasn't changed. You've preserved the solution set. But there are exceptions, right? You can't multiply both sides of an equation by zero or divide both sides of an equation by zero. And if you square both sides of an equation, you run the risk of introducing extraneous solutions. In other words, you think, yeah, I can square both sides of this equation, but it turns out that that doesn't guarantee that you preserve the solution set when you do that. So this might become an issue if you're integrating both sides of an equation. So let's get into it. So we want to solve the following equation. And this, I've written it in this form. This is a differential equation. Uh, so dy dx is equal to some function of x, g of x, divided by some function of y, f of y. And we've got an initial condition, y of x naught is equal to y naught. Okay. So the first thing we're going to do is we're going to cross multiply. We're going to get dy times f of y is equal to g of x dx. And then we're going to integrate both sides of this. Now, what we want is, well, what is the solution of this differential equation? Well, it's y is some function of x. And so we're going to do this formally. Now, when someone tells you that they're doing something formally in mathematics or in an equation, what they really are saying is that we're going to follow the rules to the letter of the law, but we don't know whether it's legal or whether it's really going to work. And oftentimes they start a proof like that. Formally, we'll do this and then we'll see what happens. Well, so formally, I'm going to integrate both sides. On the left, I'm going to integrate with respect to y, and on the right, I'm going to integrate with respect to x. Now, that should cause you some concern because you're not doing the same thing to both sides of the equation. Okay, well, let's do it. So integral, and let's say formally we're integrating with respect to y. So integral from y naught to y of f of y dy is equal to, and on the right side integrating with respect to x, so x naught to x g of x dx. Now the reason I'm doing it this way is to make it clear when we're going to use the fundamental theorem of calculus in a moment here. So we have an integral with a variable upper limit and a constant lower limit. But again, I want to emphasize that what we have here is an integral with respect to y on the left side and an integral with respect to x on the right side. And if you're the least bit skeptical, you might wonder whether this is legal. So, okay, now what we're going to do next is we're going to differentiate both sides with respect to x. Now, before I do that, notice that this is the implicit solution of our equation, y as a function of x. In other words, what we have here, here's our y. And when we go through this whole process, whatever it is, integrating both sides and doing the integrals, simplifying, what you're going to end up with, hopefully, is some function y as a function of x. And that is our solution of this equation. So if this is legal, and so let me actually put a little red question mark here. if this is legal, then we'll get the solution of the differential equation. And that's what we want. Okay. Well, so I said what we're going to do is we're going to differentiate both sides with respect to x. So let's go ahead and write that. So d by dx of the integral from y naught to y of f of y dy excuse me is equal to d by dx of the integral x naught to x g of x dx. Now we're going to use the fundamental theorem of calculus. Let's do the right side first because it's a little easier. Since we're differentiating with respect to x, and x is our upper limit, and this is a constant, we can immediately write down that the answer is g of x with x substituted, so that's still g of x. So we get g of x on the right side. On the left side, you got to be a little careful here. We're differentiating with respect to x, but y is the upper limit of the integral. And so what we have to do is we have to apply the chain rule because we're differentiating with respect to one variable, but we really want to differentiate with respect to another variable. And I could write all that out, but I think you know what the chain rule is. And so I'm going to write this as f of y. So that's the d by dy of this integral. So f of y, but then we have to follow up with multiplying by dy dx. And so let me just put this in a place where it's more obvious what's going on. And now if we divide both sides by f of y, we get dy dx is equal to g of x divided by f of y. And lo and behold, that is our original equation. And so we know then that this y is a solution to our original equation. Now, what was y? Well, it was implicitly defined by this formal operation of integrating both sides of the uh, separated differential equation. It may seem a little bit like smoke and mirrors, but it's not. This is a proof that you can integrate both sides of an equation with respect to different variables and get a solution to your equation. I hope this has been helpful. If so, please like and subscribe, and I will see you in the next video.